Here we tackle topics relating to space exploration, including technology, engineering, and futurism. I'm your host, Thor. Our first episode will treat the topic of lunar colonization over the next 150 years.
Mr. Vice President, Governor, Congressman Thomas, Senator Wiley, and Congressman Miller, Mr. Webb, Mr. Bell, scientists, distinguished guests, and ladies and gentlemen. I appreciate your President having made me an honorary visiting professor, and I will assure you that my first lecture will be very brief. I am delighted to be here, and I'm particularly delighted to be here on this occasion.
To accomplish our goals in the time we have, I've organized today's content into 3 segments. First, an assessment of extant lunar exploration technologies and related technologies, along with justifications for associating them with lunar exploration. Second, we'll look at a timeline of socioeconomic development of a realistic near-future Earth and its active relationship with the Moon. Finally, we'll examine the workings of a hypothetical moon colony using investigative rationales for our propositions. Humans went to the moon using both established and emerging technological development, and over the course of our handful of visits to the lunar surface, the requirements of these technologies did not drastically shift, while our priorities as a species evidently did. The proven Apollo launch vehicles and support systems would go virtually unchanged throughout the lifetime of the Apollo program, with only experiments and payloads they carried becoming more complex as we grasped the challenges of exploring Luna with intensifying grace and tenacity. From understanding locomotion in lunar gravity to experiments utilizing lasers and field measurements, each experiment intentionally led to another in rapid succession. When people wonder why lunar exploration has stagnated in recent decades, they may logically conclude that perhaps the experimental data to be gained was a diminishing return on the investment of the Apollo program. Some attitudes of key persons within and with direct influence over NASA might even reflect this notion, but as with all things in space exploration, the circumstances around the decline of interest in lunar exploration were far more complex than any single explanation in hindsight can provide. There is, however, a good explanation for the recent resurgence of Luna as an exploration goal, both in the eyes of the public and institutions, which also ties into the reasons for its original decline. Luna never faltered in its ability to provide experimental data in a broad context, but the goals of space exploration for a time have not made Luna particularly attractive over alternative research missions in orbit and beyond. Considering we've spent most of the last half-century developing our access to orbit technologies, as well as long-duration manned orbital flight, it's fair to conclude we've been busy paving the way to cheap and sustainable space access as a means to reduce those formerly astronomical costs of accessing a body such as the Moon. This brings us to the future of Luna's role in the further development of space technologies, and the topic of this video. Treating this topic fairly will require a thorough look at the near and far future of the Moon. To frame a complex thought experiment, we'll approach the topic with one goal in mind: to navigate the problems in reaching and sustaining 5 million adults living on the Moon's surface as permanent inhabitants. You may be wondering, why 5 million? That's an enormous figure, dwarfing hypothetical Martian colonies for our century. The Mars Society in February of 2020 announced a competition to design a self-sufficient 1 million population Martian city-state to serve as a reference model for the first steps to colonizing the Red Planet. Today we're discussing higher stakes, and there are two reasons for this. Firstly, this is an experiment to establish what is possible with a commitment to our future as a civilization. Nothing discussed here is impossible given our trajectory as a species, and to these ends we will take a close look at the necessary scale of space exploration efforts to accommodate our goals. The other reason for using a goal of 5 million residents is to simplify the concerns typical of futurism thought experiments. These are questions we often ignore when outlining colonization timelines of other worlds in casual discussions, but at the same time are known factors in affecting the success of space exploration. They are, broadly, social factors and concept accessibility. I'll explain both of these ideas since they represent fairly nuanced problems. Planning coordinated activities between nations, private corporations, and emergent organizations is notoriously challenging. When contextualizing history in terms of space exploration, the reasons for striking out have been urgent and are usually tangible, but those reasons shift and revolve with geopolitical and economic pressures. Social factors play a central role in space exploration, and a marked deviation from any colonization's initial goals and plans should be expected. In our situation, this is actually a feature, not a flaw. A colony needs to be able to think for itself and act on its needs in ways potentially undermining any established goals. Likewise, the capabilities and goals of any entities enabling this effort are likely to change over colonization timelines. This notion is not that difficult to work with, since we can look to historical and modern parallels for cues about how emergent societies can be expected to behave under relative isolation. By extrapolating out to 5 million residents, we can simplify the unpredictability of both the emerging lunar and established Terran societies, by conceding both have met their respective and evolved goals mutually. This is not a dismissal of relative challenges and divergence, but rather a self-aware way to navigate the ultimate product of this relationship between future Earth and a colonized Luna. People are generally unwilling to support an endeavor if they are unfamiliar with its core concepts, highlighting the need for experimentation and hypothesis. We must also recognize the difficulty of establishing a realistic thought experiment we can apply known challenges to. 5 million humans sharing a fairly centralized economy is an accessible juncture comparable to the largest cooperative urban societies to exist today. I would argue half this number would be prone to instabilities suffered by similarly scaled economies on Earth today, and any more within a magnitude of difference would essentially be an extrapolation into the more distant future of the systems 5 million would accomplish more quickly. After all, we aren't trying to model a hand-picked planetary population of overqualified personnel, but a vibrant human society with an independent culture, industry, immigration, consumerism, and an accessible economy. Our lunar society ought to be comparable in physical scale to the ones we know today in order to have a grounded discussion, so we'll maintain normal population densities and forego modeling a few major self-contained population centers. Multi-million inhabitant arcologies and the like are a viable option on the moon, but we have no examples on Earth of such an engineering project, so we'll use proven limits. Imagining a colony of 5 million allows us to work from easily found and evident social and economic information, without also limiting ourselves by directly modeling any particular small society. So before we begin our study in earnest, what are some other important implications of 5 million adults on Luna? We can dismiss any dialogue where the surface has been relegated to automated industry. Luna is, for our purposes today, a fully fledged colony intended to seat the human race as well as provide resource access. While there are good arguments to be made for never settling the surface of the moon with large populations, there are some equally good reasons for doing so. These colonists will be almost exclusively adults. Children will be most likely not able to develop safely there without normal gravity. Unless habitats replicating normal gravity become preferred, ignoring their inherently greater cost, youth will remain in orbital habitats until their bones are fully developed. Establishing a large society on any other stellar body beyond Luna presents the hurdles of communication lag, more expensive and time-consuming transit, and local isolation. Each of these factors cannot be dismissed on their own, and together represent an existential threat to any human colony at every challenging junction. I will argue any logistical limits a spaceborne society will face, such as resource access or growth pressures, become impossible to quantify beyond what we can glean from our own largest societies here on Earth. That being said, modern industry and social policy have proven many of the challenges faced by our species during its defining periods are no longer long-term threats. While this may sound like I'm describing a point of balance, where the colony will likely never break down after exceeding the 5 million resident goal, I don't see this as a cusp, but rather an intermediate lying between what we can reasonably estimate given our experience as a species, and a mysterious future filled with questions as to the ultimate fate of our species' relationship with the cosmos and ourselves. Challenges will arrive, and lives will be threatened by formerly unknown problems, but many of the old problems endemic to this world will be far behind once a lunar colony is established on this scale. Now we can focus on what technologies we'll dedicate towards this project.
For every victory gained, you will also suffer a defeat. If you know neither the enemy nor yourself, you will succumb in every battle.
Utilization of the moon suggests or mandates the development of a set of technologies currently in their infancy. These include and are defined as ISRU, the tech, hardware, materials, and systems involved in converting local environmental material into usable resources needed by human presence, expansion, and scientific operations. Low-gravity industry, the redesign of agricultural and industrial activities for a microgravity and low-gravity environment, ranging from discrete engineering problems to broad economic structuring. Regolith construction techniques. An ability to use the lunar surface's equivalent of dirt with minimal processing is an essential aspect of lunar construction and architecture towards the goal of inexpensive, energy-efficient, long-term structures. Portable fission. The role of small nuclear fission devices in powering the tools for settling the moon and providing inexpensive energy to its industries and inhabitants will require continued private development of related technologies and adaptation for the microgravity environment. Long-range telecommunications. The considerations of communication distortion, time lag, and lunar telecom infrastructure are fairly well understood but not yet applicable. There is undoubtedly much to be learned along the way as telecommunication continues to expand in its central role in human society. Meteorite protection. The measures we can take to protect human activity from the destructive effects of meteorite bombardment on Luna, either actively against anticipated objects or passively against emergent threats. Dust mitigation. The methods by which accumulation of lunar dust and its detrimental effects on mechanical and electrical systems can be minimized. It's worth noting ISRU and low-gravity industry have more overlap than other topics, as both deal with fluid reclamation, heat transfer, and ventilation in microgravity. Now we'll take a look at each of these concepts in detail, starting with ISRU. Long-term moon colonies of any scope will rely on local resources to subsist. In situ resource utilization, or ISRU, refers to the technologies, systems, and infrastructure needed to convert the materials distributed in a foreign environment into useful products. These products run the gamut of anything a colony might need to exist: water, various ingredients for concrete, ferrous and silica construction components, fuel, human consumables such as atmospheric constituents, substrate, soil, and fertilizer chemicals. These are all desired products which can be partially or wholly extracted from the lunar environment. The lunar regolith is known to consist of a few useful compounds in large amounts, with volatiles and other materials of interest either in trace amounts or scattered irregularly on and within the surface. Their relative concentrations are approximated on this table. Most of these elements are present as compounds, notably silicate compounds and aluminum and iron oxides. Molten regolith, or oxide electrolysis, and carbothermic reduction are the two most studied ISRU processes currently. Both are sustainable processes which do not require other materials, only energy. Molten regolith electrolysis is a variation of molten salt electrolysis, a widely used industrial process for producing metals. Regolith is made molten, and from it oxygen, gas, and liquid metals are extracted. Carbothermic reduction uses focused light or a laser to produce oxygen from regolith with or without water ice present. Water is arguably the most valuable resource of all, not only for its role in sustaining biological life, but because water can be converted into fuel via electrolysis or used as a fuel component directly by spaceships with onboard fuel refineries. Unlike Mars, there is no guarantee of increased concentrations of water within the Moon due to its stagnant core. Therefore, the most realistic method we can plan for is to extract water ice via heating or chemical processes. We know some lunar locations have water and volatiles in relative abundance, such as the poles. As is often discussed, these sites are dangerously cold, even for the most advanced modern automated systems. The temperature can reach as low as negative 150 degrees Celsius in complete shadow. Establishing the infrastructure to accomplish this task of obtaining water will be the first priority of any moon settlement, and as we've discussed, the most viable method initially will be to process large amounts of regolith. Later on, we'll work over the energy cost of procuring this vital resource on a realistic scale. The lack of both an atmosphere and major geologic activity creates a challenging prospect for those expecting traditional mining operations on the Moon, be it open pit or tunneling. Below the lunar regolith exists discrete masses of lunar rock, increasing in size with depth. This is the result of eons of meteor impacts shattering the hard surface and depositing the finer material across a wide area. Mining into this geometric lattice creates a real threat of unpredictable destabilization and collapse of surrounding areas. Moonquakes would be devastating to any mining operation or colony, so until we can afford to reinforce mines with strong walls, we must rely on trawling surface deposits for ISRU resources. Next, we'll look at low-gravity industry in the context of industrial fabrication. With the introduction of a 3D printer on the ISS in 2014 from Made in Space Incorporated, the current limitations of microgravity production are already being explored. In 2019, the In-Space Refabricator was unveiled to the public, a unit using technology from Tethers Unlimited, capable of repurposing various types of plastics into feedstock and printing from them directly. It accomplishes this without grinding the material, allowing the plastic to be reused multiple times, and it can utilize hard polymers, soft plastics, and even plastic film. The recycling ability of the unit surpasses any other 3D printer on Earth. With significant advances in additive manufacturing over the last decades, we've seen these and related technologies being applied in commercial rocket manufacture, notably SpaceX's Super Draco engine. Lunar manufactories will certainly represent a step into unfamiliar ground for any industry, but we can cite those Earth industries with similar goals and capabilities to understand where we can apply our strengths in the opening stages of settlement. The initial goal will be to assemble a manufactory capable of replacing all of its own components from available materials. Once this level of flexibility and parts tolerances is accomplished, further endeavors can be more experimental in nature. Advanced manufacturing techniques such as laser sintering offer distinct advantages over traditional metallurgy techniques, since it can be performed using a powdered metallic medium, saving time and energy in converting regolith into usable material. Deep-sea welding and construction experience promise to offer a working analogy for construction on Luna. Unsurprisingly, these conditions are already simulated in test facilities among space programs. Human labor will be directly involved in the construction phase for a long time to come, as artisan labor has proven to be more reliable and applicable than automation for many demanding manufacturing tasks in even the most advanced industries. There have been experiments on the International Space Station to grow herbs, tubers, vegetables, and small trees in microgravity, all with good success. Growth of food crop variety plants has been remarked as unusual compared to a full gravity environment, but is entirely viable. The interesting feature of plants grown in space is their ability to genetically self-regulate, activating genes that provide guidelines for stem growth when normal genetic instructions reliant on gravity fail to produce results. As with many genetic mechanisms, how this process is regulated is not yet well understood. Plant tissues, relying on capillary forces, seem largely unaffected by changes in gravity, and in general other plant growth mechanisms do not appear to be inhibited from a microgravity environment. Light source direction is the determining factor for root and leaf growth direction, not gravity. On Luna, partial gravity will permit the use of materially efficient deepwater culture and substrate hydroponic methods. Providing the root system with resistance in the form of substrate or flowing water will enable food crops to exhibit growth virtually identical to their native environment, although the difference in question is largely aesthetic. Plants with a low degree of vertical organization are preferable, since they are spatially economic. Miniaturized versions of common food crops are widely available today and fit the needs of a budding lunar farm perfectly. Next, we'll discuss regolith construction techniques. There are numerous strategies for making regolith into viable construction material. The simplest has been employed by humans for thousands of years, using water, any particulate rock, and a fine cementing material, with most variations of this aggregation commonly referred to as concrete. The Cement Trust, an organization which tracks the role of concrete production throughout the world, states that concrete is the second most consumed product on Earth after water, with nearly 3 tons of concrete produced each year for every human on the planet. The construction needs of a budding lunar colony are thus solidly evidenced by our behavior here on Earth, a place where highly developed and developing nations consume construction materials at a startling rate. Concrete represents one of the simpler technological hurdles for settling the moon, since we can substitute a range of imported materials for a binding agent, including polymer, ash, and silica processing byproducts, of which a lunar colony would have an ample supply. Polymerized construction materials on the moon do not need to be as durable or strong as on Earth, as there is lower gravity and no random variations in temperature to cause unplanned thermal expansion. Concrete on Earth is stabilized by gas bubbles, but this would be a detriment rather than an advantage on Luna, where methods to remove these bubbles would be implemented, either by vibration or electrical charge. Our next topic is portable nuclear fission. The World Nuclear Association states, small modular reactors, or SMRs, are defined as nuclear reactors generally 300 megawatts equivalent or less, designed with modular technology using module factory fabrication, pursuing economies of series production and short construction times. The potential of recent innovations in small-scale portable fission power generation cannot be overstated. The Westinghouse Company recently unveiled its plans for the eVinci, an innovative liquid metal reactor with power outputs from a few hundred kilowatts to 20 megawatts per unit. This design is a departure from even the most compact reactors currently in service. It has no moving parts in its coolant loop, no valves, and no turbines. It is thus advertised as solid state. Most SMRs are portable enough to fit into standard shipping containers, including support and backup equipment. They accept a flexible range of feedstocks, including low-pressure gas. The development of these reactors for commercial markets has required their respective companies to develop power substations along the same design parameters as their reactors, meaning a group of independent reactors can be continually expanded while using a common substation to distribute their energy. A framework to house each of these subassemblies can be easily standardized and swapped out without wasting space or mass. This modular and scalable system is without a doubt a perfect fit for an expanding moon colony's needs. You might understandably be cautious to assume this technology is fully realized. After all, many vehicles such as submarines and carriers carry fission reactors, but this does not necessarily translate into a technology we can expect the private sector to develop and implement on its own. You may be surprised how successful and widespread portable fission has become today. Germany, Russia, and the United States have employed these modular systems for well over a decade, and the latest state actor addition to the Portable Nuclear Power League, Iran, has demonstrated the viability and accessibility of this concept in a developing economy. The Nama Madpazargard Industrial Group launched their first portable generator in 2016, after a development and construction period of just 6 months. This allowed Tehran's energy sector to reduce overall costs by 80% over similar imported plants. This indicates much of the costs associated with these systems is in development, licensing, and sale. Fast forward to 2019, and Iran just established its largest yet mobile power plant in a disaster relief role, consisting of 5 truck trailers with 4 producing 2.5 megawatts, and the 5th serving as a self-contained electrical substation. Hoping to wean itself off of reliance on fossil fuel in the near future, Iran is a perfect environment for the application of these technologies and demonstrates their potential and ease of commercial implementation. The Moon has a nearly instantaneous communication delay with the Earth. A message takes about 1.2 seconds to reach the Moon, and another 1.2 seconds is needed to send a reply. A priority phone call would take about 2.5 seconds to get a reply. This is comparable to time lag using voice-over IP services between distant locations here on Earth. Communication delay is not something which can be improved, since it is dependent on the speed of light. There will, however, need to be improvements made to the bandwidth capacity for such long-range transmissions using powerful directional broadcast equipment. Energy will, for a time, be a highly in-demand resource on Luna, and any improvements to telecommunication efficiency and digital security will be important. A lunar telecom constellation will inherit different considerations than those satellites orbiting Earth. Earth's magnetic field offers a degree of protection against solar radiation for most satellites, meaning lunar satellites will need to be more robust and protected. Secondly, without an atmosphere, lunar satellites will not deorbit in the same way as satellites in low orbits around Earth do. Terran satellites are generally designed with a specific lifetime in mind, after which they deorbit from atmospheric interaction and burn up to reduce orbital debris and make way for newer, better satellites. Lunar satellites will still eventually deorbit, but the driving mechanism is irregular gravity, not drag. The irregular density of Luna's interior causes unpredictable satellite motion, and until an accurate, high-resolution map of Luna's gravitational field is created, satellites will need to make unforeseen station-keeping maneuvers to remain in orbit. While Terran satellites tend to be light and small, with chemical thrusters to account for predictable decaying orbits, lunar satellites will be semi-permanent and expandable, with the need to interface with other craft more frequently because of their permanent nature, as well as potentially needing refueling. Lunar satellites that do require deorbiting will probably do so in order to land and receive maintenance and upgrades, likening them more to traditional spacecraft in function. Making restartable engines capable of cycling on timelines of years with enough power to land and ascend from the lunar surface is possible even today. A lunar satellite may well prove to be the ideal testing platform for future outer solar system exploration craft, carrying powerful restartable engines with long-term power self-sufficiency and low-loss two-way communication capabilities. Objects that cannot maintain an orbit around Luna will inevitably come crashing into it at high speeds. This brings us to meteorite protection. The moon's surface is under constant bombardment by micrometeorites, traveling at speeds up to 65,000 meters per second, and with no atmosphere to resist them, all exposed surface structures must be hardened and protected accordingly. Objects in the wake of comets represent the high end of this risk curve, but mercifully arrive on predictable schedules. The Leonid streams are one such notable example, causing dramatic annual meteor showers on Earth as a result of the comet Tempel-Tuttle's 33-year orbit into the inner solar system. The specific span of time when impacts are most likely can be ascertained by observations from Earth or the Moon, making random dangerous events statistically unlikely. The severity of seasonal showers parallels those on Earth, so one year may involve mere hundreds of potentially threatening objects, while the next year delivers tens of thousands. As the threat of impacts is ever present, a risk system will need to be devised in order to limit EVA activity across the Moon during peak meteor activity. A planet-wide hazard rating system could be implemented, which would limit human surface activity to essential tasks during high-risk periods, a sort of storm warning system. Active protection measures against these risks include ground-based missile batteries and lasers for large meteorites. Lasers can be used on objects detected which have a greater proportion of water ice, and missiles for rocky objects. Lasers are viable for meteor defense on the Moon due to the absence of a gaseous atmosphere, which would interfere with the laser beam on Earth.
All radio is dead. Which means these tape recordings I'm making are for the sake of future history.
Most micrometeorites are very small, and contribute to a different problem: dust. Lunar dust commonly refers to the finest particles of the lunar regolith, which has many unique properties compared to any dust or soil counterpart we have here on Earth. The challenges posed by this dust stem from both its material and how it's created. Unlike organic soil, created through dissociation of organic material, erosion, and sedimentation of rock, lunar soil is created entirely by mechanical forces, as the Moon's surface is barraged by fast-moving debris. That's not entirely true, actually. The process is a bit more complex. There are two distinct mechanical processes and a third irradiation process which contribute to the dust's properties. For our purposes, understand that lunar dust is mechanically abrasive and irritating due to microscopic irregularities. Moon dust presents an array of problems to an early settlement due to its toxicity and fine particle size. There are two aspects to lunar dust to consider: creating active dust and managing static dust. Active dust is that which is mobilized by electrostatic charges or agitated by human activity or meteor impacts. Static dust is dust that was active and has settled on a man-made structure. An interesting concept for passive dust mitigation is impregnation of structural concrete with carbon products, allowing the application of an electrostatic charge across large structures, effectively repelling and cleaning them of dust. Lunar EVA suits might take advantage of air overpressure to keep visors and grip areas free from static dust as well. Now that we've covered the expectations of our thought experiment, let's have some fun and imagine what Luna will look like as we move towards our determinations. We'll glimpse two different dates in our near future and realistically evaluate the current trajectory of space exploration as it relates to our experiment, as well as a few key developments on Earth, and then we'll jump ahead to our fully fledged colony to examine its composition and capabilities. I would urge viewers who might consider going into this level of detail a move towards idealization to keep an open mind. The development of space exploration technology, while historically full of instances of delays and cancellations, has a steady and predictable trend out to a point. Regardless of your familiarity with the capabilities of current launch vehicles, I hope this timeline will put you into the mindset of establishing a realistic potential future for humankind in space. The year is 2045, and prominent celebrities and political leaders have visited orbit for extended periods, broadly supporting charities and medical research as interest in space exploration continues to grow. The ISS has received its third private expansion using modules supplied by Bigelow Aerospace. NASA, in close cooperation with United Launch Alliance and Blue Origin, as well as SpaceX, the ESA, and CASC, have each established interdependent and cooperative avenues to the Moon's surface, frequently sharing personnel and resources outside of Earth's orbit. This is the beginning of the first economy outside of Earth, with each party bargaining and bartering for fuel and consumables during mission planning. The cost from Terra to low Earth orbit has fallen to its lowest yet, at just under 1,000 USD per kilo. The cost from Earth geostationary orbit to Lunar surface is between $150 and $400 per kilo, depending on whose orbital infrastructure is chosen. The options each offer distinct advantages, with SpaceX being the least expensive per kilo and with a range of high-capacity crew-rated vehicles. The ULA, Blue Origin, and NASA's joint endeavor offers better options and support for complex, repeatable missions. Due to ULA and Blue Origin's close interactions with the project responsible for NASA's presence on Luna, formerly known as the Lunar Gateway, and subsequently the Artemis program, their framework is generally viewed as the preferred choice for lunar private manned missions and colony preparation projects within and beyond the United States. SpaceX, however, has achieved the first tangible step on this path, landing 35 people on the Moon for 15 days as a proof of concept. These US-based options continue to be the preferred routes for the budget-minded throughout the world, although China's space program is on the cusp of finalizing an entirely independent infrastructure consisting of 6 separate stations. These include a single module station in Terran geostationary orbit, a refueling hub at the Terra Luna L1 Lagrange, scientific and habitation hubs at the Terra Luna L5 and L4 respectively, and 2 diverse multi-module stations in lunar orbit. From these stations, China has reserved spots for visitors, researchers, and commercial payload from Japan, Russia, England, Vietnam, Egypt, the UAE, Iran, Algeria, France, India, Australia, and Thailand. India and China have begun closely cooperating to develop their launch capabilities further, both currently utilizing the GSLV Mark III and Long March 7 rockets, respectively. The Luna Society, in cooperation with the Ansari X Prize Foundation, just concluded its second Moon Access competition, and to date over a dozen universities across the globe have delivered scientific payloads to the lunar surface, most of them using the X Prize platform. The most resounding success of the 2042 Manned Lunar X Prize competition was a 24-hour visit of 2 students from the Indian Institute of Technology in Madras, who conducted experiments and an EVA on the lunar surface. The year is 2070, and the commercial global leaders in space exploration employ a lineup of powerful heavy-lift vehicles to reach the Moon's orbit and surface. ULA uses the Vulcan Centaur 3 heavy and light variants, upgraded versions of the proven Vulcan platform with crew-certified upper stage capable of carrying Boeing's Starliner capsule atop 3 BE-4-powered reusable cores. The Centaur 3 can also be configured with a single core powered by either the BE-4 or an RD-196 and up to 6 GEM 63XL SRBs. ULA also employs the Atlas 6 Starliner, a 5.4-meter fairing workhorse of the ULA with a proven track record. It is a revival of the Atlas V and has a highly configurable first stage with reusable SRBMs. Additionally, the Atlas 6 Lunar liner is the newest iteration of the Atlas platform revival, upgraded with a nitrogen RCS system and an extra-wide upper stage, employing a double or triple engine mount and a 6.2-meter fairing. The European Space Agency and Arianespace, in conjunction with NASA's Commercial Crew Development Program, have developed the Ariane 7 version C3 and version C2D. These are crew-rated capsule-carrying versions of the Ariane 6, with an updated reusable launch abort tower developed by SpaceX through the ongoing Commercial Crew Development Program, compatible with a range of capsules from various international agencies, including the Orion, the Orbital, the CST-200 Starliner, and Crimson Dragon. The upper stage operates either an Orion service module, a Centaur 3 with 2 or 3 engines, or a Centaur 5 with either 1.57 or 1.62 meter fairings. International launch services, with Roscosmos and the United Rocket and Space Corporation of Russia, have developed the Angara HA-7VL and HA-7PL, the newest, heaviest variant of the Angara family to date, and a direct evolution of the A-7V, produced in both a crewed and uncrewed configuration. The crewed vehicle utilizes an Oral Crew capsule. Both vehicles utilize a hydrogen-powered KVTK-A7 upper stage. The vehicle is not intended for a descent to the lunar surface in a crewed role. HA-7s are launched at the Domovoy ultra-high capacity staging facility of the Baikonur complex, Pad 52, currently the only launch site available for the HA-7 family. The Angara HA-7 can be configured with between 2 and 6 strap-on recoverable boosters using the RD-180 engines around an RD-196 powered core. The China Aerospace Science and Technology Corporation, with the China Academy of Launch Vehicle Technology, has produced the Long March 7, the latest heavy lift vehicle in the Long March series, with a payload capacity of 37 tons. The Indian Space Research Organization, with the Antrix Corporation, have developed the Lunar Gaganyaan launch vehicle, or the LGLV Mark I, an extensively configurable design for high-frequency travel to lunar orbit at a commercially viable cost. It consists of a 3-stage 140-ton core and 4 220-ton SRBs. The LGLV is the first vehicle in ISRU's lineup to employ a dual cryogenic upper stage. Also available is the Geosynchronous Modular Launch Vehicle, GMLV Mark V, an extension of the GCLV program intended to add a high-power restartable upper stage for recoverable vehicles and delivery of scientific payloads beyond Earth orbit. NASA produces the SLS Block II, a designated platform for the Orion capsule, utilizing 4 RS-25D engines to power its first stage and 4 reusable advanced SRBs. It is capable of mounting a Crimson Dragon capsule for limited orbital activities using a specially developed ferry module mounting 8 Super Draco engines, acting as a service tug. The SLS Block 2B Cargo is a 152-ton configuration of the proven SLS Block 2, with 5 additively manufactured RS-25EA engines powering its first stage. First stage is configurable for up to 4 reusable advanced SRBs as well. Blue Origin utilizes the New Glenn Ampla, the second iteration of the New Glenn Heavy Launch Vehicle, powered by 11 BE-5 engines, with a reusable first and 7-meter diameter second stage. It is a commercially successful rocket boasting a quick turnaround time and broad payload options. The Japan Aerospace Exploration Agency, along with Mitsubishi Heavy Industries, produces the H-3, a 2-stage expendable launch vehicle with 4 SRBs and a first stage powered by 3 LE-7A engines. SpaceX produces several vehicles. The Falcon 11 Super Heavy is a high-capacity configuration workhorse of the SpaceX fleet, with a range of engine and payload options. It features fuel cross-feed capability and reusability of all boosters and first-stage core. The Interplanetary Starship 1 is a cargo variant of the Starship, with unpressurized and pressurized options. Starship 1CB includes the option to mount a Crimson Dragon module in an extended upper fairing. The Interplanetary Starship 2 is a crew-rated variant of the Starship, with a tethered counterweight for spin gravity during deep space missions. It has served its first crewed outer solar system mission successfully as of 2064. While there are over a dozen discrete landers employed by various nations and agencies around the world, few capsules are used for regular crewed descent to the lunar surface. These vehicles, each with distinct advantages and limitations, are the Blue Moon Heavy, mounting the Orion and CST-200 Starliner capsules, Interplanetary Starship 1CB and Starship 2, mounting a Crimson Dragon capsule and native vehicle capabilities, respectively. Both vehicles can perform Terran returns with refueling. And finally, the Boeing HLS, an expendable lander mounting a native return vehicle. In the year 2070, there is near constant traffic between Terra and Luna orbits, amounting to roughly 850,000 kilograms of payload capacity, or 935 tons total. Roughly 70% of this mass is commercially viable, and the remainder is allotment for supplies and consumables for station keeping and government programs. Cryogenic fuel production has been subsidized within the United States for national industries and to international interests via broad economic development subsidies in and outside of the US. As a result, cryogenic fuel has become virtually free use by any US-based company space-side, so long as they can access them. This dramatic reduction of the barrier to entry to space pressures similar moves by both China and France. There are numerous parties interested in bolstering this arrangement, and organizations begin offering the fuel resources remaining from safety margins and routine supply missions to the various nations and entities they share infrastructure with. Mission planning becomes easier with each new launch anywhere in the world, as international cooperation becomes a reliable factor in mission design. Bigelow Aerospace has commenced work on the first privately owned lunar orbital station, following successful deployment of 3 B-330 habitat modules aboard the original Artemis 2034 station. The United States' newest military branch, The Space Force relinquishes its presence beyond Earth orbit as a global effort to police interplanetary space is organized between China, the United States, Russia, France, and India. This results in the formation of the first cooperative global military police force, the Deep Space Transit Authority. The Outer Space Treaty of 1967 is amended to permit the policing of interplanetary space, and this revision is passed by all participants unanimously. With the Tiangong 12 being launched atop the new Long March 9, China has completed their lunar geostationary station. Further additions to the station will be accomplished by private endeavors by India, South Korea, and Japan. The ISS continues a decade of historic expansion, with modules from 5 different nations added, including a nuclear fission reactor module and a vehicle fabrication bay. The first primate born on the Moon, Coral, has become the unofficial symbol of humanity's lunar efforts. Over 97% of humanity are witness to a broadcast of Coral's first hours of life. There is an immediate uptick in public interest, as SpaceX sells out of tourist seats aboard their fleet of 4 interplanetary Starship 2 passenger vessels, each with a capacity of 60 people to lunar orbit. The lunar surface is home to between 1 and 300 humans by mid-2070, mostly researchers and a few tourists. To date, the largest population to inhabit the lunar surface at once was 1,231 people during the Olympic event of 2072, including 50 athletes. Colonization of the Moon is underway in earnest, with permanent structures being erected at an increasing rate. 5% of electrical power on Luna is provided by nuclear fission, 95% by solar. The goal is to transition to 15% nuclear power by the end of the decade and to 50% by 2095 to accommodate larger construction projects and permanent launch facilities. At the forefront of space development discussion is the need to expand launch infrastructure across EU member nation states. This is an echo of existing efforts to complete the updated, state-of-the-art Koroni launch complex in Greece, a site which has suffered cost overreaches and delays since it was began in early 2054. Russia later that year reopens the Baikonur Cosmodrome's 41 launch complex, 110 launch pads, and the Site 250 static test stand, locations which had been left disused for nearly a century. Historians begin to argue that humanity is entering a new epoch, indicated by the unrestricted reach of the internet into every country and home on the planet. The urgency of accelerated space exploration becomes a central political topic as the frequency of climactic and health crises appears to be increasing yearly. The year is 2170. And before we look at ongoing developments on the lunar surface, we need to glance at installations in orbit and condense their capabilities and roles. We'll overlook objects beyond stationary orbit, those in so-called graveyard orbits. Since we first began exploring lunar orbit, we noticed unusual orbital behavior compared to missions to other astronomical bodies. We now understand the Moon's density is irregular, with massive nodes called mascons causing considerable variation in gravitational forces acting on objects in low orbits. Since the orbital period of objects under 100 kilometers tend to be around 2 minutes, gravity causes a cascade of orbital deviations which quickly prove fatal for unpowered craft. Mapping the variable gravitational field of the Moon is essential to the development of our lunar colony, and low-orbit communication satellites use this high-resolution field map to maintain frozen orbits requiring very little station keeping. For vehicles with short stays in lunar orbit and manned stations, there are a few orbital inclinations which are almost exclusively used. These inclinations have been dubbed the Lunar Freeway, and virtually every routine manned mission makes use of one of them. In our first look at the settled surface, we'll examine the infrastructure and major construction projects of our lunar colony, starting with infrastructure. There are 6 major settlements across the moon's surface, accessing numerous research and mining sites distributed across an otherwise sparse lunar expanse. Solar power transmitters have been placed at every 30 degrees of longitude at the equator and at the 40th parallels. These serve as aids for navigation and emergencies and are maintained by automated rovers. With 3 bases located equidistant along the equator and 1 near each pole, most spacebound traffic utilizes 5 major launch complexes. They are Quericos, Mitso, Turina, Oyam, and Ugria. These facilities are multi-level structures, extending between 2 and 5 floors beneath the lunar surface. They each feature limited manufacturing capabilities, elevator launch pads, independent mission control centers, service structures, and some have underground berthing capabilities. The largest launch site, Turina, houses 270 permanent residents and promises the ability to turn around a fully maintained and refueled Starship 2 every 3 days, or 1 crewed lander per day. The ability to renew landers on Luna as well as Terra at multiple sites has benefited the continued development of these vehicles in respect to their efficiency and crew comfort. The immediate 75 kilometers around each major launch site is zoned for minimal development for safety. Freight and passengers are shuttled by maglev trains to urban industrial centers nearby. Suborbital traffic is also a widely utilized option, since heavy payloads are relatively inexpensive to relocate quickly across the moon. Local suborbital traffic and supplies are distributed between many lesser landing pads, ranging from concrete complexes replete with exhaust channels and dust mitigation systems to simple plots of makeshift hardened regolith surface. Sites of significant industrial development include the Aristarchus Crater, the Oriental Basin, the Taurus Littrow Valley, and the Amundsen and Shackleton craters of the southern lunar pole. The near-side equator and the southern pole are the most developed, spanning the moon's most valuable and accessible real estate. Construction is disproportionately in favor of the moon's near side, since early colonization was simplified by line-of-sight telecommunication with Earth. A high-speed maglev train spans the entire equator, branching into hubs all over Luna. There are a total of 27,000 kilometers of magnetic rail on the moon, although a large portion of this distance consists of parallel tracks. Maglev transportation offers numerous advantages over the alternatives, requiring little infrastructure maintenance, low initial costs, and a proven safety record. The rail's robust design allows them to electrostatically repel lunar dust passively at some energy cost, or actively along lesser-used sections by clearing them just before they are traversed. Materials for maglev rail can be sourced from the lunar environment, and the need for strong magnets is reduced due to low gravity. This equatorial maglev system serves as a starting point for the long-awaited Lunar Star Tram, based on the concept developed by James Powell, father of the maglev train, and Dr. George Mace, hypersonic vehicle specialist from the Brookhaven National Laboratory. This concept employs a powerful maglev rail confined within a vacuum tube. The rail accelerates a spacecraft to orbital velocity and beyond. The propulsive core of this system is a long linear electric motor, making it an extremely efficient path to orbit from the moon. The implications are apparent. An uncrewed vehicle launch track uses higher accelerations and thus a shorter track. Crewed versions require smaller impulses of energy and are longer given lower accelerations. The track can effectively be hundreds or thousands of kilometers long, depending on the elevation of its starting point and payload tolerances, as well as local gravity. The Lunar Star Tram overcomes material challenges of building a similar system on Earth, where a strong gravitational field and dense atmosphere dominate the path to orbit. The Lunar Star Tram does not require extravagant support structures and bypasses the need for a vacuum chamber, kilometers in length, and a plasma gate to contain the vacuum's open end. This is a component representing significant energy costs to the system as a whole in discussed concepts. The Star Tram concept applied as a lunar project is conceivably a very inexpensive and rapidly deployed option, which quickly recoups its payload cost as a fuel-efficient alternative to traditional launch escape vehicles. Next, we'll take a look at the human aspects of our lunar colony in two distinctly interrelated areas: human requirements and industrial capabilities. Starting with human requirements. Fundamental human needs are considerations for long-term physical and psychological health, and they include shelter, exercise, water and food, clothing, a clean atmosphere, social avenues, and varied available activities, and those can be subdivided into leisure or work activities. These requirements we will use to compartmentalize the multifaceted task of keeping humans alive, and they can be represented as a spectrum of the overall human experiential need. Needs are often overlapping ideas, so we'll organize the human demands as ranging from decidedly concrete to arguably abstract. On the microscopic end of the spectrum, we have spatial needs, the physical volume and consumables required by individuals to perform daily activities and to rest independently. Social, the availability and frequency of social locations and interactions. Cohabitative, the ability to act on a desire to form close bonds and to share spaces as desired. Communal, the flexibility of physical and information networks to accommodate organized tasks and the continuation of cultural practices. Commercial, the demand for goods and services. And finally, an encompassing aspect worth strong considerations is Terran biology, and by extension, environmental optimization. A requirement for natural flora and fauna is difficult to evaluate within the spectrum, since humans have demonstrated an innate ability to function outside of our evolutionary environment, equally as well as we did when it was the only option. Terran flora will exist necessarily in order to balance our ecosystemic and dietary needs, and fauna will exist probably as a novelty at first, and later as an extension of our various tangible needs beyond Earth, either as comrades, livestock, or a signature of cooperative human life, and likely all three. Let's start on the individual end of our spectrum of human requirements, with spatial needs. The International Space Station will serve as a case study for several of our purposes here. It is the closest analog worth contrasting human spatial needs while in relative isolation. Numerous studies have demonstrated how humans behave in isolated habitats here on Earth, but nowhere other than the ISS have so many people of varying ages and physical characteristics inhabited a microgravity environment together. Since Luna has about 15% Earth gravity, spaces will not need to be designed with total freedom of movement in mind. This simplifies imagining interior layouts, which will be comparable to traditional living spaces, but also means pressurized volumes will not be as efficient per occupant as a similar volume might be in microgravity. We'll err on the side of overestimating spatial needs when comparing to the ISS for this reason. Pressurized spaces are at a premium away from Earth, and only consumables and frequently accessed hardware should occupy the interior habitat. The issue of stowage inside pressurized spaces is simplified on Luna compared to the ISS, since cargo may easily be suspended in simple netting on ceilings and walls without risk of falling or shifting from movement of the habitat. Consider when we evaluate the area needed on a per-person basis, we are including walkways, passages, closets, toilets, kitchens, and other communal areas. The ISS is a space intended for a crew of 6, with 915 cubic meters of pressurized volume. From this distribution, we'll estimate a person needs around 150 cubic meters of space, although this number decreases with more residents, since many areas are shared. We'll maintain that residential spaces will require 150 cubic meters under 10 inhabitants, and shirt-sleeve workplaces will require 100 cubic meters for up to 20 occupants. A person on Luna will utilize about 3 to 5 liters of water, hot and cold, per day. One water source can serve up to 5 people comfortably, and at least 10 if not being used for activities like bathing. Water is not used for eliminating human waste, and very little is required for hygienic activities. rinseless shampoo, edible toothpaste, and changes to the hygienic regimen can be used to bring water consumption even lower. Water is relatively easily obtained on the lunar surface, but as is the case anywhere, it must be considered precious. According to simulated regolith heating experiments carried out at the Glenn Research Center, about 200 watts of power are needed to convert small masses of hydrated regolith into usable water by simple water ice melting, and this does not include the energy of acquiring and transporting the materials. Using the notions we've established, let's model a minimum efficiency habitat for 12 occupants. We'll call it the MILS, short for Minimal Immersed Lunar Living Station. The MILS is an underground cylindrical habitat 17 meters in diameter and 5.5 meters tall with a domed roof. It has a single entrance with an airlock and a loading ramp extending to the surface. The airlock is contained within a small room extending from the side of the habitat with a compartment for cleaning EVA equipment and suiting up. When multiple mills are in close proximity, an unpressurized conduit connects each habitat above ground, greatly reducing dust from traffic between them. As with all long-term lunar living spaces, the mills is buried several meters beneath the surface, with a hardened concrete layer in addition to its roof structure. The roof of the habitat is made from a prefabricated aluminum honeycomb lattice. The lattice is assembled on site from linked sheets of pre-cut aluminum and then filled with a concrete slurry. The low gravity and vacuum conditions allow this material to be foamed to a high volume for its mass via gas injection. To construct the mills, the lightweight honeycomb dome is lowered onto a circular wall section dug into an excavation site. The dome is supported by tubular spokes which converge around a central support column, a hardened structure which encompasses a short-stay storm cellar. The dome is then buried under regolith. Several concrete light ducts extend to the surface and reflect filtered light into the habitat. They can be closed to passively regulate temperature as well. The mills includes 4 discrete 500-liter water storage tanks, a wastewater treatment unit with a throughput of 200 liters per 24-hour cycle, a backup treatment unit with a 125-liter capacity, and a 2,500-liter sump tank, which also serves as the storm cellar's shielding. Since the mills is minimally protected against radiation, it features a small space surrounded by water storage to offer quick and convenient radiation protection for its inhabitants, should the need arise. A project site with multiple mills would utilize an additional surface access water storage tank with gravity-fed pipes for improved redundancy. Each resident has a spacious private room with a centrifugal bed, shower, and personalized workstation. There is a shared recreational area with a diner, lounge, theater, and studio, as well as a fitness room. The innermost volume of the habitat also has considerations for entertaining work and exercise. The unpressurized conduit connecting each habitat above ground greatly reduces dust from traffic between them and to nearby work sites and surface facilities. This allows daily visitation between habitats, sharing of the recreational facilities, as well as providing social variety. However, the mills is not a permanent residence, but more akin to a worksite dorm. Larger habitats, housing thousands or hundreds of thousands, will have social considerations play an active role in their design and layout. Shared spaces are not only essential in a human sense, but are economic in a design sense, since social locations imply physical proximity. We will have to change how these spaces are perceived in order to offer private spaces as a guaranteed, personalized opportunity in large habitats rather than as individual necessities. As we move away from the outpost model of the mills and consider larger population, we find the unique challenges and considerations of lunar habitats as we will examine them today. Epicenters of populations up to 1 million, settings where our goal of 5 million humans on Luna become tangible. Let's illustrate a hypothetical living situation in a self-contained habitat of 750,000 people. which in terms of our 5 million makes it a medium to large size settlement representing 15% of the total lunar population. Keep in mind this is a scalable facility, which is designed, as with all urban centers, to accommodate expansion well beyond its initial capacity. We'll call this complex Moonbase Alpha. Besides berthing facilities, raw resource storage, and small observation domes, the entire complex is underground. The majority of Moonbase Alpha's internal volume consists of 4 separate domes, linked by shuttles and walkways. Each dome is 60 meters tall and 340 meters in diameter. A direct comparison to understand this scale is the O2 in London, formerly the Millennium Dome, which is 52 meters high and 365 meters in diameter. One of the 4 domes has the capacity for approximately 1.35 million cubic meters of pressurized space and 20 primary levels. Altogether, Moonbase Alpha can conceivably total over 2.2 million square meters of usable floor space, with each inhabitant representing around 2.9 square meters or more. These figures obviously pose intimidating logistical questions. While excavation of the Moonbase Alpha site and erection of the structural dome are grand but technically simple tasks, assembling millions of square meters of material appropriate for human habitation is a challenge. We'll take a brief look at the methods I propose to accomplish this. First, retaining walls are put up in place and compacted regolith bricks are placed as a foundation. The load-bearing dome is dropped in as segments over a skeletal frame which is later removed. After the dome is established, the ground floor is heat-hardened and covered in thin layers of self-sealing UV-cured polymer. A work tent is inflated across the entire ground level, providing a small pressurized space for humans and equipment to begin the interior work inside. The gaseous environment itself becomes a structural component at this point, used both to maintain rigidity and as a construction material in the manufacture of concrete and aerogels. Aerogels consist of expanded hydrated silica gel, which is then supercritically dried, causing their liquid components to be replaced by gas.
Measurement owes its existence to Earth.
Silica aerogel is a thermal insulator, fireproof, extremely lightweight, is relatively simple to manufacture, and has configurable properties. Aerogel can be manufactured as small, solid blocks or processed into flexible sheets. In the situations we envision, the potential to pour raw material into molds and directly finish the product into its final forms using vacuum and heat is of huge implication. While aerogels are more expensive than other materials, sufficient use of them can substantially reduce the structure's wasted heat. For our purposes, the aerogel is hardened by addition of rigid fibers and waterproofed to the required specification. A thin, high-tensile rigid polymer or aluminum skin is applied to the aerogel to mitigate impact deformation where needed. Stringers and pylons are used to maintain a rigid overall structure. Walkways and work areas utilize aluminum and steel, while walls and light-use flooring utilize high-tensile treated fabrics and flexible aerogel insulation. This means most of the interior walls of Moonbase Alpha are nearly paper-thin and slightly flexible. By the year 2170, a moderate level of internal development towards Moonbase Alpha's full potential can be expected. Let's assume the 12 lower and therefore largest levels have been completed in each dome, with a rubberized pressure skin containing atmosphere where pressurization is needed. This brings us to about 1.8 million square meters of usable walking area and 2.4 square meters of footprint per inhabitant. The actual space mandatory per person for sleeping versus daily life differs, since sleeping chambers are designed to maximize use of volume within the spacious stacks of Moonbase Alpha. Each person uses a small space with a centrifugally spun bed and simple hygienic station no larger than 1 by 1 by 2.5 meters. This room is used exclusively for sleep, and all other activities are accommodated nearby. Importantly, these sleeping units can be stacked to maximize spatial efficiency. Central corridors connect thousands of sleeping chambers to restrooms and customized multi-use rooms, which vary for single users, pairs, families, and groups. These rooms focus on providing relaxation, light entertainment, and privacy. Larger communal rooms tailored to specific recreational and leisure activities would be offered, either by availability or reservation, depending on activity during peak times. Another solution to maximize efficiency would be to have rotating shifts. While half the colony sleeps, the other half works, essentially cutting in half the demand for bunks. The opportunity and freedom to pursue dependent or intimate relationships is a key aspect of human life and should not be overlooked. On Luna, there is one major concession to the standard practice of building a family, which, as mentioned before, complicates planning pregnancy and upbringing. Unless underground facilities providing artificial gravity become economically feasible, children will not be allowed any extended stay in the low lunar gravity due to developmental issues and the inherent risks of routine commercial spaceflight. That is to say, birth and upbringing may be relegated to orbital nurseries where gravity can be maintained long-term, or may simply be mandated to occur on Earth. A medical consensus will need to be established and proven to determine a safe allowance of low-gravity hours per year at various stages, and modified on a per-child basis. This all hinges on whether children traveling to the lunar surface ever becomes a commonplace event, enough to requisite accommodating infrastructure. With these considerations in mind, planning a family will become a consequential course of action, requiring strong commitment and greater long-term planning than is generally practiced on Earth. In the context we are using the term, a communal human requirement implies two different things, at least. First is the ability of a complex society to form and maintain physical and information networks in order to accomplish organized tasks, and the second is empowering individuals and groups towards the continuation of their cultural practices. Maintaining information networks occurs naturally in all human societies historically, and the widespread technological advances of lunar settlement will likely precipitate an even faster and more meaningful organization of social groups at all levels. If modern times are any indication, the value of communication will continue to expand as the physical gulfs between individuals and societies grow into the solar system. Essential human pastimes can be reimagined and innovated upon in the lunar environment. Cooking and brewing will be reimagined as the behavior of their components in low gravity shift radically. Since atmosphere and light are at a premium, humans and food crops will share spaces wherever it's viable. The proximity of food crops and living spaces within lunar colonies implies most people will play an alternating role in maintaining these gardens, and practical botany will become a valued and widely learned skill. Fine arts such as dance, sculpture, exercise will necessarily be a central aspect of lunar life, and physical fitness will likely shift in its tangible meaning, as both aerobic and high-intensity workouts with limited available calories are required to maintain health. The low-gravity environment of Luna promises interesting opportunities for exercise and entertainment to overlap. Adrenaline and acrobatic hobbies are certain to provide great entertainment value in low gravity, such as martial arts, biking, skateboarding, rollerblading, and paintball. Traditional sports will need to be reinvented. An angled track and resistant gearing would allow a fairly identical analog to bicycling on Earth. Certain ball games could provide a basis for lunar adapted varieties, such as squash and paddle tennis, while most other games using a ball could be adapted by simply increasing the ball's weight to compensate for gravity. Using physical space efficiently in the manner we've prescribed when discussing Moonbase Alpha will be crucial to bringing commercial growth potential to the Moon. This doesn't imply basic services should have a transactional cost, though, and such a system would not be sustainable. Given the clear capacity of the colony to provide essentials such as energy, water, and basic food, attaching an individual financial burden to these resources is counterproductive. Virtually no consumable materials are wasted on Luna by design, and 100% of waste products are reused. Energy would also not be constrained on a per-user basis due to the negligible impact of individual activities on the colony's net energy utilization. The fundamental commercial opportunity at Moonbase Alpha is increasing its population, and this is why maximizing space is crucial. Our colony is home to 750,000 people today, but could potentially house twice that number even before expansions to the actual complex's footprint. As supporting infrastructure grows, the incentive to offer a low-cost home at the colony does as well. More occupants means more commitment to long-term lunar presence and continued exploration of the solar system and the utilization of its riches. It goes without saying, space offers a retinue of new commercial ventures which dwarf even the most ambitious historical commercial developments of Earth. The larger a pressurized volume is, the easier it is to manage environmental conditions long-term and maintain pressures and temperature as the number of occupants and their body heat varies. These volumes are subdivided into areas, with differing specification depending on their utility. We will need to maintain an appropriate environment for the needs of various areas of a large lunar settlement. Dry areas are areas providing access to transportation networks with heavy foot traffic between living quarters and functional spaces. They would need to be kept cooler and less humid to limit dust mobility, reduce perspiration, and minimize wear on electrical interfaces. It's possible small motorized vehicles will be used in these environments, so these spaces will need good airflow design and regular maintenance to ensure they are conducive to good health. Temperate areas are areas where food is consumed and social gathering and recreation take place. Air temperature is variable depending on the activities, and humidity is kept at a universally comfortable level. Humid areas are areas where plant life thrives and a Terran natural environment is being replicated. This might include flowing water, soil, pollinating plants, and animals. Air circulation and humidity are kept high to support flora, and temperatures and lighting mirror Terran seasonal and daylight cycles. The capabilities of our lunar colony for industrial activity will, for our purposes today, be identified as the capabilities required to maintain the colony's positive growth. Each industrial component of human lunar civilization is closely interrelated, but we'll begin our analysis with water. Our colony will require access to 75 million liters of clean water on a daily basis solely for human consumption. This is mostly a one-time investment, since all of this water is recycled continuously. Thus, all energy expenditures by the settlement after procurement of its initial water needs are energy costs associated with water treatment. Some industrial processes requiring water will, however, not be recoverable, such as in the manufacture of building materials. The unrecoverable constitutes a small portion of even these tasks, though, since these processes can be optimized to recycle a part of their water consumption. Seeing how concrete can be aided by plasticizers and the water-to-cement ratio is not a constant, we'll consider that each human on Luna requires a plot of concrete, 1/3 of a meter thick, and as large square as the minimum area they will need to live in a minimally scaled and thus inefficient habitat, which we calculated earlier as approximately 18 square meters. This estimation is an attempt to acknowledge the concrete-based infrastructure needed to support human activity, as well as the structures they inhabit. While the drying behavior of concrete is different on Luna, there is little information available to inform our discussion on this, so I'll use the standard ratio of 0.4 kilos of water per kilo of cement. Even if this is not ideal, it is certainly possible to reach this ratio on Luna, with manufacturing even without the use of fluidity-boosting polymer additives. Such additives provide a shortcut for large-scale projects with minimal water use requirements. 5 million people on Luna will require approximately 27 million cubic meters of concrete, amounting to 10.8 million metric tons of water. While this is a worthwhile consideration, it is certainly an overestimation for our concerns. 27 million cubic meters is enough to cover 7% of the lunar surface in a centimeter of concrete, to provide scale for this figure. Even with our envisioned monorail circumnavigating the lunar equator, this is a massive allowance for our thought experiment, and is intended to demonstrate the upper limits of our problem. In order to accomplish the task of amassing this volume of water over the course of 100 years, we'll need to produce an average of 295 metric tons of water per day from the year 2070 to 2170. Considering we have 50 years to start this process on our timeline, this is not an impossible task, especially if our economy and launch infrastructure is robust enough to supplement these needs with water ice from the asteroid belt and even excess fuel. The launch infrastructure we've established on our timeline can easily accomplish this demand and more. The lunar surface regolith is believed to hold anywhere from 10 to 1,000 parts per million of water ice, although this figure is highly debated. The potential for high water concentrations in some areas continues to be a driving force for renewed interest in lunar exploration, and this may constitute a true game changer. There are currently two primarily considered ways to extract water from the lunar surface. Both are being investigated in lab tests, although their large-scale yields are difficult to estimate. Erring on the side of caution, extracting 1 ton water per 1,000 tons of processed regolith is hardly viable, so we'll need to prospect for caches of water ice left from comets and natural formation under the lunar surface, which is an understood phenomenon. We've mentioned lunar mining is dangerous due to the composition of lunar geology, so this effort would need to be isolated and perhaps automated. However, mining water ice as hard as granite is not absolutely necessary with the right technological applications. Microwave radiation can be used to penetrate lunar permafrost and free water vapor with extremely high efficiency. Laboratory testing boasts that 98% of available water can be collected using this method. Another method being investigated is the chemical addition of hydrogen to regolith at high temperature, a process which frees oxygen from the abundant iron oxides and leaves behind usable iron dust. The disadvantage associated with this method is reliance on access to a supply of hydrogen. Given this method also generates a supply of iron, it is, however, of particular interest. There is thankfully a more convenient option which has been the focus of lunar colonization debate for quite some time. Water ice has been spectrally observed in surface deposits near the poles, and in polar craters receiving no direct sunlight. Such deposits could provide millions of tons of easily accessible water ice. Much as the situation was 20 or even 10 years ago with these techniques, we simply don't have hard data to say how much water ice is held in the lunar permafrost. In comparison, since Mars has water on its surface, the question of water there has always been more obvious than in the case of Luna, where the existence of water ice was debated for years as we lack the technology to detect it hidden just below the surface. I will say I am personally optimistic about this topic, since every development towards assessing lunar water ice has leaned towards the expectation of there being much more than the previous model would ever indicate. Luna's power needs are provided by two sources, solar and nuclear. Solar power requires a relatively large quantity of limited resources for its power yield, whereas nuclear power is also provided by imported systems, but has a much greater output by cost. Nuclear power has virtually no maintenance costs associated, while solar panels require constant cleaning and regular replacement. Solar is further exposed to the micrometeorite barrage of the lunar surface, while nuclear generators of all sizes can be buried and protected from the elements. These factors have introduced solar as a rapidly deployed solution for limited power needs, and nuclear as a standard for long-term power generation for colonies, industry, and launch infrastructure facilities. Unlike material demands, energy demands are met relatively easily on the lunar surface by scaling up operations with continual missions from Earth, which do not suffer sluggish returns on investment. Where solar has inherent costs associated, nuclear is a one-off expenditure for any investor. The greater barrier for energy needs would be power transmission over large distances, which necessitates costly boosters and kilometers of buried cable. Energy production is not prohibitive, and these demands can be met with today's technologies. The components of industrial-scale agriculture, including carbon, nitrogen, phosphorus, and other minerals, will be produced on Luna by its inhabitants. As the number of lunar colonists consuming prepackaged foods increases, the usable soil capacity increases. Agricultural activity is carried out inside habitats using extant atmosphere and light sources by rotating shared responsibilities between all colonists. The exact demands of our lunar colony are difficult to approximate, since nutrition imports are likely to play a large role in feeding the population for at least 100 or 200 years. However, this import relationship will probably be an economic concession, since the efficiency of modern hydroponics will permit early lunar self-sufficiency if required. It is more likely that space where agriculture might be sustained will be put towards more economically viable tasks for the initial phase of settlement. Lunar colonists will need to exercise regularly, and caloric needs can be individually regulated since exercise is a controlled aspect of daily life. All essential nutrients and caloric intake is provided by fruits and vegetables, nuts and grains, fungus, or insects. Each person requires 250 grams of vegetables or fruits daily, with 5 to 20% of calories derived from fats. We'll assume a 2,500 calorie diet is average. For any calculations, we'll provide an additional 50 gram leeway, since some foods are more nutrient dense and filling than others, and to permit proper protein consumption. We've already mentioned colonist water use, and we have allotted 14 liters of water per person per day. While we've generously provided this amount, it's worth noting the crews of Apollo, Skylab, Shuttle, and the Shuttle Mir programs consumed between 1 and 4 liters per day. This is a stark difference, and these intakes were not sustainable but acceptable given the duration of these missions. Malnutrition and kidney damage would be an issue for longer missions. Feeding our moonbase Alpha and its 750,000 people will require some 225 metric tons of food per day. To contrast, the Berlin airlift of 1949 required 1,500 to 2,000 metric tons of food supply per day, and over double that amount in coal. This amount could be entirely imported from Earth if needed, given the commercial payload capacities we've established, but we have 5 million mouths to feed, so this approach is not viable in the long term. We'll need to break down the individual nutrient sources for an average meal to establish how quickly edible material can be grown. I've chosen flexible food crops with specific nutritional values to represent a total diet of our lunar colonists. We'll examine the fertilizers, volume, and energy required to sustain a few key examples, and from there approximate the industrial footprint of lunar agriculture. Mushrooms grow extremely rapidly and require little light to produce. They can be processed into a variety of textured food products. A modern industrial mushroom farm with skilled labor produces at most 75 pounds or 34 kilos per square meter per harvest. That may sound like a lot, but this figure is in line with the most modern commercial farms in North America today. Harvests can be done once every 3 weeks, followed by growth media conditioning. Fruiting bodies of mushrooms require very little space relative to soil, and around 6 garden beds will fit into a space 1 meter in height using traditional practices. This allows a yield of 450 pounds or 204 kilos per cubic meter per harvest. Mushrooms have 2 requirements for industrial scale cultivation: chemical inoculants and soil components. They do not utilize chemical fertilizers, but instead rely on aerobic composting processes. Soil occupies around 30% of the growing volume, not including the inert growth medium. Therefore, about 367 kilos of soil are required per meter of growth volume. During composting, 5% by weight of inoculant and soil amendments must be added, totaling just over 18 kilos of additives per compost cycle. Sunflowers are one of the fastest growing nut options available, providing proteins and fats. All parts of the plant are edible. Considering we cultivate them similarly as on Earth, we can achieve 20 plants per square meter, and 4 layers of 250 centimeter tall plants per cubic meter. This yields 80 mature plants per cubic meter in around 90 days. This implies 10 pounds or 4.5 kilos of sunflower seeds. The entire plant is edible, so total usable mass is approximately 650 pounds or 295 kilos, not including roots. When expressed as a monthly yield per cubic meter, this is around 217 pounds or 98 kilos of food material per month, of which 3.2 pounds or 1.5 kilos are seed. The primary fertilizer constraint around sunflower and indeed most vegetable plant crops is nitrogen. Around 11 kilos of nitrogen are required per meter of growth volume, assuming the soil has zero nitrogen content to start with. Continual growth on the soil will reduce this demand. For each meter of growing volume, 0.25 cubic meters of soil weighing 306 kilos are required, assuming a 12 by 4 by 4 inch volume of soil per plant, supplemented with minimally processed silicate substrates. These 306 kilos of soil are a one-time cost, since further replenishment is accomplished by fertilizer additive. The aforementioned nitrogen fertilizer demand of 11 kilos is a seasonal figure, representing depletion of the soil after consecutive harvests. Since all runoff from watering is reused, there is very little unnecessary loss of nitrogen in the system. Insects can tend to produce the greatest return of proteins and fatty acids for space, time, and energy required. Many edible species exist, allowing a highly flexible harvest period and feedstock requirements. For our considerations, we'll look at crickets, which are a complete protein source and are already widely cultivated on Earth. They are a perfect choice for feeding lunar colonists, either whole or ground into a powder. Crickets reach adulthood in about 1 month and thrive off human food waste. They do require a high calcium diet, so their total feed demands are represented as 5% added calcium, 40% food production waste, and 55% meal. Crickets require around 2 kilos of feed per kilo of meat. Unlike our other crops, feed mass is more of a constraint than growth volume here, since crickets can be cultivated in extremely compact spaces. Spirulina can be cultivated within water storage sumps, used for other aquaculture and hydroponics operations with minimal additional energy. Spirulina does not require living energy or an organic carbon source to grow. It is our final item for the agricultural study and the simplest to consider due to few needs and rapid propagation. Spirulina requires several minerals to grow, and of them, sodium bicarbonate represents the majority. For every kilo of dry spirulina produced, an approximately equal amount of bicarbonate-based feed is needed. Now that we've established the resource demands and footprints of a selection of crops, let's assess Moonbase Alpha's ability to commit to self-sustaining agriculture. 68 metric tons of insects, 45 tons of spirulina, 68 tons of mushrooms, and 45 tons of sunflower are to be produced daily to feed 750,000 people. Insect farming has a relatively small physical footprint, just over 2,400 cubic meters. To feed them will require 3.4 metric tons of calcium and 37.4 tons of feed from grain. Sunflower farming will occupy 13,800 cubic meters, the most spatially demanding crop we could have chosen. About 55.2 metric tons of fertilizers are required annually, with 3 harvests per season. Keeping with our model, this is 38 kilos of fertilizer per day. Spirulina aquaculture will piggyback off the agricultural water supply, and so does not add significant dedicated volume to the existing systems. Fresh spirulina would require 7 metric tons of sodium bicarbonate-based feed per day, and an equal weight of the dried product demands closer to 40 tons. The distinction here is wet crop can be harvested rapidly and consumed directly as a vegetable, where the dry product must be dehydrated and consumed as a nutritional additive. Mushroom farming will occupy 3,300 cubic meters and is harvested routinely by mechanical pickers. This implies just over 1,200 metric tons of composted soil are required. Unlike fertilized crops, this soil must be cycled out of the system physically several times a year and conditioned before being reintroduced. When this occurs, 60 metric tons of soil amendments are added to the composting process. Altogether, agricultural industry for Moonbase Alpha stands at around 19,500 cubic meters. This is 1.4% of the total volume of the habitat, and is equivalent to 7.8 Olympic swimming pools. Until a lunar biosphere is established where usable soil is plentiful, Moonbase Alpha will requisite about 54 metric tons of supplies per day. The Orion capsule, in comparison, weighs 33.5 tons on the launch pad with launch abort system. Mushrooms and soil-grown crops will require a facility to process soil and compost to sustain them, and one large facility can provide for most or all crops simultaneously. It's worth noting that soil preparation is a time-consuming process, but can be greatly accelerated at the cost of energy. Fertilizers, and more importantly, hydroponic systems, remove the need for composted soil in food production, but relying on chemical fertilizer is not a viable long-term use of our available resources. Compost soil will be readily available on Luna, and will be utilized to recycle expended nutrients. The high productivity of hydroponic systems will be used to supplement stockpiles and rapidly produce typically slower growing crops, not as a replacement for traditional agriculture. There are many methods for maximizing vertical space use with soil-grown crops. I propose for Moonbase Alpha to employ a novel technique of soil-filled plastic tubes arranged at varying heights. With this method, tall plants can be grown on top of one another without compromising root density or light exposure. Now that we've fully explored our thought framework for colonizing Luna up to the goal of 5 million people, and we've provided solid examples for all different scales of human habitation on its surface, you might be wondering, what about exploration beyond the moon? Surely with these launch capabilities and this effort, there's a substantial amount of exploration occurring beyond the Terra Luna system. Other celestial bodies and potential exploration strategies will be the topic of future episodes. If you found value in this content, consider taking steps to support and share the channel with others. This has been your host, Thor, now signing off. Thanks for watching.